I think one of the most incredible things, I have to talk to you about this, one of the most incredible things that humans have ever accomplished is LIGO.
Hmm.
We have to talk about gravitational waves. And the very fact that we're able to detect gravitational waves from the early universe is effing wild to me.
It's crazy. Yeah.
Can you explain what gravitational waves are? And we should mention you wrote a book about the humans,
Yeah.
about the whole journey of detecting gravitational waves, and LIGO, Black Hole Blues is the book. But can you talk about gravitational
Yeah.
waves and how the hell we're able to actually do it?
Let's just start with the idea of gravitational waves. I have to move around a lot of mass to make anything interesting happening in gravity. I mean, if you think about it, gravity is incredibly weak. I mean, right now, the whole Earth is pulling on me, and I can still get out of this chair and walk around. Like, that's insane. The
Yeah.
whole Earth. Gravity's weak, right? So to get something going on in gravity, I need like big objects and things like black holes. So the idea is if black holes curve space and time around them in the way that we've been describing, things fall along the curves in space. If the black holes move around, the curves have to follow them, right? But they can't travel faster than the speed of light either. So what happens is as black holes, let's say, move around. Maybe I've got two black holes in orbit around each other. That can happen. It takes a while. A wave is created in the actual shape of space.
Mhm.
And that wave follows the black holes as the black holes are undulating. Eventually, those two black holes will merge. And as we were talking about, it doesn't take an infinite time, even though there's time dilation, because they're both so big. They're really deforming space-time a lot. I don't have a little tiny marble falling across an event horizon. I have two event horizons. And in the simulations, you can see it bobble, and they merge together, and they make one bigger black hole, and then it radiates in the gravitational waves. It radiates away all those imperfections, and it settles down to one quiescent, perfectly silent black hole that's spinning. Beautiful stuff. And it emits E equals mc squared energy. So the mass of the final black hole will be less than the sum of the two starter black holes. And that energy is radiated away in this ringing of space-time. It's really important to emphasize that it's not light. None of this has to do literally with light that we can detect with normal things that detect light. X-rays, form of light, gamma rays are a form of light, infrared, optical, all this whole electromagnetic spectrum. None of it is emitted as light. It's completely dark.
Mhm.
It's only emitted in the rippling of the shape of space.